Take a look at our couple examples here. All right, so rate of change is still the topic of the chapter. It's still on derivatives and how to use them and kind of like what's the purpose of them. The ones that you had in your homework, I'm going to do two. There was one with the natural log, this one, and then there was one with an e.
Yeah, definitely.
I want to talk about those two because I said last week I'd cover them. So let's talk about those first. So the question of the day was talking about finding a critical point. Right, and an inflection point. I think this one wanted both, I think. So, what you have to do this, to find the first derivative. Okay, so let's do the first derivative of this problem. Okay, so again, we're just reviewing a couple of these homework problems. Okay, so, first derivative of this thing, it is a normal power rule in the beginning. So the normal power rule is just 5. Then you have a minus sign and a 3. And the natural log, the derivative of it, is just 1 over whatever is in its parentheses. So it's 1 over x, and we're taking that times 3, because the 3 is just hanging out up front.
So it could be 3 over x.
It could be 3 over x if you want to write it that way. So this is what we're going to get. So it ends up being 5 minus 3 over x. Now, that's the first derivative. That's how you do natural logs. Now, if that x was anything more complicated, it would be multiplied on the back like a chain rule. But we don't have anything. X is just a 1 anyways, we can take the derivative of it. Now, to figure out the critical points, you still have to set this thing equal to 0 and solve it. So I would add the 3 over x across to the 0, multiply the x across to get it off the bottom, and divide by 5. So there is one of your critical points. Again, that's simple algebra 1. You add the 3 over x over to the side so it's not negative. You multiply the x across to get rid of it off the bottom, and then you divide by 5. It's inverse operations to find x, with least amount of steps. That's the easiest way I can explain it to you. That's how I would do it. Again, for every critical point.
Find the second derivative.
Second derivative. Okay, so second derivative is pretty straightforward. So this is where we're at on the first derivative, right? This is where we ended. To find the second derivative, the 5 would go away. That's gone. Oh, I shouldn't put an x there. It looks weird. So when you take the derivative of 5, it's gone, right? It's just 0. That's gone. Now the derivative of the fraction is derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. That's how you do the normal derivative, right? I just consider the top to be a negative 3. That's what I just consider the top to be. So the derivative of 3 is 0. It's still negative, but that's going to go away. So this ends up being, the second derivative ends up being, so if this turns out to be 0, that's gone. So I'm left with a negative 1 times negative 3, which is positive 3.
Factor into this at all, or no?
No, because the 5 was out front, right? You're just doing a normal addition rule. So derivative of the front.
Is it negative 0 or what's
So,
that just
yeah, it's a negative 0 because it's just derivative of negative 3 is 0, and it's got a negative sign on it, so it didn't matter. And then over the bottom, which is x squared. So that's the second derivative. Yeah, and so if you didn't hear Isaac, he was talking about what happened to the 5. That's a normal sum and difference rule. The sum and difference rule for derivatives is you just take the derivative of each item separately and put the minus sign in between them, right, or plus sign in between them. So the derivative of 5 is 0, it's gone. And then we have the back, and we take the derivative of the back thing by itself. So if we set this thing equal to 0 to solve this thing out, we set this thing equal to 0. And there's pretty much no way of getting this thing equal to 0. Just think about that. If you were to plug in any number into that x squared, you're not going to get 0 out of this thing. Even if it was a decimal, and you plugged it into x, you'd square it. It'd just be a decimal, and you're taking 3 divided by decimal, which is a really big number. If you plugged in negatives, the negative signs would go away. There's no way to actually make a 0. To prove my point, you'd multiply the x squared over.
I was going to say, don't you just
and you get this, and that doesn't work. That isn't even true, right? That 3 doesn't equal 0. So this thing doesn't have an inflection point. It doesn't change, from concave down to concave up or anything like that. So there's no concavity change. So there's no inflection point. So it really only has an inflection point on this one, or a critical point, sorry. Only
Oh,
has a
there's
critical
just
point.
NA.
Yeah. Yep, so, yep, non-applicable, yeah. NA. Okay, all right, questions on that one?
Will you go over the beginning quick? I missed that.
The first derivative,
Just the first line, second line.
this line right here,
Yeah, sure.
or
Just
up
I
here?
understand it.
No.
The
First
green or the yellow?
First green.
The first green
I
line,
was,
the derivative of 5x is 5,
okay.
and the derivative of that -3 natural log x, the derivative of natural log is just 1 over whatever's in that
Okay,
variable.
that's what I was looking for.
Yeah, and so the 3 just stayed, because the 3 didn't matter.
Okay.
I'm done.
That help you out?
Yeah.
Okay.
Those kind of things scare me, so I never
Yeah.
understood them.
Yep. Okay, any other parts of that? That was good?
Out of this.
Okay, all right, let's go to the next one. So the next one was this item, right? That was the next one, right?
Yeah.
He is the man.
All right, so derivative of this thing. So let's do first derivative. First derivative of this, it is a product rule. There is a multiplication sign between them, even though it didn't show it. It's 4x times e to the x. So it's derivative of the first. So I'm gonna separate them like this. That's the two parts, first and second part. So when I say first, you know what I'm talking about? I'm talking about the 4x. I'm talking about second, I'm talking about e to the negative, or e to the 3x. Okay, so derivative of the first times the second plus the derivative of the second item, which is this. Now, how I'm getting that? Because derivative of e to the x, or e to the 3x is e to the 3x, but then you have to take it times the derivative of the 3x, which is 3. So it's like a chain rule. And then you take it times the front. So it's derivative of the first times the second plus the derivative of the second times the first. So, so that's what we get. If I want to figure out what this thing, what makes a critical point, you set this thing equal to 0. So I'm going to set this, so I'm going to take this thing, set it equal to 0. I'm going to simplify this thing a little bit. Just, is that outside or is that a phone? Oh. All right. Anyway, so we set this thing equal to 0. Shh. So we set this thing equal to 0 to solve this thing to figure out the factors.
What's right there? Open the
Okay.
shade.
No. Hey. So we I don't care. So we're gonna factor out e to the 3x, and so when I factor that thing out, I have a 4 plus 12x.
Yeah, it's here.
No, it's going by.
Okay. All right.
Oh.
Yep, it's going that way. All right. So, okay. So I factored out e to the 3x.
Break out the nursing home.
Shh. So e to the 3x, we have the 4 plus 12x. What would make these things equal to 0? Because I've already factored that thing apart. I noticed that they had e to the 3x. In fact, I could have pulled out a 4 if I wanted to. If I want to pull out a 4, I'll put a 4 out here, and this would have ended up being a 1 and a 3. That way it got rid of the 4s there. So to make this thing equal 0, there is no possible way of doing it. Just to prove my point that I can't make that thing equal 0, I set it equal to 0, and I solve. I divide the 4 over.
So
which is
basically,
that.
if you have ln or e, there's not going to be a point.
Yeah, there's just no way to make it 0, because even on that problem, when you take the natural log of e to the 3x, you can't take the natural log of 0. I don't think it works in a calculator. Natural log of 0, I think it's undefined. Yeah, it's an error. It's not possible to do it. Because think of it this way, there's nothing that I can put in a power of, like, e is 2.7, right? So if this is 2.7 to the 3x, there's nothing I can plug into the power of a 2.7 to make that thing 0. Like, I can get it smaller, but I can't make it 0. I can just get it really close to it. I just can't get it there exactly.
Thank goodness. So we really, when it's like that, we can just put no inflection point.
Yeah, there's no critical point on that. This is still the critical point. Then on this part here, on this part, I set this part equal to 0, and this thing can actually work, right? I can subtract the 1 over and divide by 3. So it actually does have one critical point, which is this thing, negative 1/3. All right. Now, if I had to do, apologies. If I had to take a second derivative of this thing, I don't know if yours had to. I think you just had to figure out the critical points on this one, right?
No, you had to find it.
Okay, so let's keep going then. So if we have to find the inflection points, that second derivative, I have to do it as a product rule. Okay, I'm gonna just wait here because I know a lot of you are still scrambling to write this down. Is there any questions with the first derivative part?
No.
Okay, all right, I'm gonna add another slide here because I didn't give enough.
There's one critical point.
Wait,
One.
how come it's 1 plus 3x and not like 1 plus
That part right there?
5? No. Oh.
Because I factored out the 4 to the e to the 3x out.
Oh, that's a different part than that.
Yeah.
Yeah, he's not doing the first.
Yeah.
You're
Yeah.
doing the first and the second.
No. All right. Are you good there, Mo? Okay, let me know when you're good. On the next, in fact, I'm just gonna freeze up to the board. All right. So what I'm gonna do now is I'm gonna go and I'm gonna write down what we left off at. We left off at this part. Now this is before I factor that thing apart. So I'm gonna go to that line in yellow. Okay, so I'm going to the part in yellow because this is the first derivative.
Why is that so unpopular? I don't know.
Okay. We good, Mo? Anyone else still need that stuff?
There's a lot of sad girls.
Okay, we good?
Yeah, no kidding. They're like,
All right.
Oh my god, this is so...
Anyone need that still?
No.
Okay, all right. I'm going to unfreeze that. All right, so this is where I left off at. That was the first derivative.
Is it called red light?
And hey, let's focus right now. Otherwise, I'm going to move on because I know how to do this. To take the second derivative of this thing, we still do it by the sum and difference rule. There's still a plus minus sign between these things. So second derivative, it's the derivative of the front item, which is just 4e to the 3x times 3, because that's a chain rule, right? You just leave the 4 alone. It's just derivative of e to the x is just e to the x times whatever the power is. So we took it times 3 because that's the derivative of the 3x. Plus sign still stays. This is still the plus sign between them. The derivative of the 12x e to the 3x, I still have to do that part by a product rule. So this is going to be in a parenthesis, and it's a product rule. Derivative of the front times the second plus the derivative of the second times the first. So I'm doing this part as a product rule.
This makes 0 sense.
Product rule?
I thought, don't you have to do the derivative first?
I already did the front. The front and
Yeah, I see that.
the plus sign separates them. So on a sum and difference rule, you do the derivative of the front item, you put the plus sign, and then you do the derivative of the second item. But the plus sign just separates them.
So it's
The
not-
second item just happens to be a product rule, so we have to do that one separately.
So it's not the derivative first times.
No, that's when you do product rule. That's what I'm about to do on the second part. Because
Within a rule.
yeah, it's a rule within a rule. Because the original problem was just two things being added together, right? That's the original problem. So you have to just do the derivative of the front plus the derivative of the second. Well, the second item happens to be kind of a bear. It's kind of a product rule. So,
Okay.
Because it's X and E.
Actually,
okay, all right. Question?
When you're going over stuff, do you ever have to like look stuff up to remind yourself how to do stuff so you don't forget anything?
Only on like weird obscure rules for like trig functions or something. Like I just don't have that memorized because when I was in college, I at least had like a formula sheet that I could go off of until test day. Then I had to like cram and memorize it because we didn't get to use calculators on our
But
tests.
now your rotation is good enough.
You
where
didn't
you
get
can-
to use calculator?
Not on any one of my college tests. They banned them because kids could program anything into them, so they just banned them from every test. So you had to
Still
have
banned?
Dude, I
in
can't
college it was for
remember
me.
my head.
So I got really good at just doing quick calculations, not adding and subtracting, but just like multiplying and dividing. I was like getting really good at it.
So that's why you're small.
That's why you're bad
So-
at adding and subtracting.
Yeah, I just didn't need to worry about it at
You
any
know, you
point.
learned it in like
So,
kindergarten.
all right, yeah. All right, so derivative of the front, 12 times e to the 3x, plus now the derivative of the second item, which is 3e to the 3x, and then that's times the first, which is the 12x. So that's derivative of the front times the second, plus the derivative of the second times the first.
Where did the 3 come from?
That is the derivative of e to the 3x. It's a chain rule. So it's e to the 3x times 3, because it's the derivative of the power.
Write it out different. Write it out how you used to write it out. You used to write it out differently. You put e to the x to the third, and then you put times 3. That's what that means.
Wait, what?
Just be Asian.
That's how I used to write it.
Yeah.
Oh, yeah.
That's
You just write it
that's the
in front.
derivative of that.
It's the same thing.
That's the same thing.
It's the same
thing.
thing, but it just looks different.
It looks like a headache.
Okay, all right. But still continuing this, I don't need to add any like terms, I don't think. Actually, the e to the 3x's can be added together. So this is 12e to the 3x out front. This is a 12e to the 3x, and this is a 36x e to the 3x. And so I can add the 12, so this is 24e to the 3x's.
Wait, hold up. Where did you get that? I got lost there.
And I'm so confused on why it's
Lost in some
It's the same.
What about?
Then why is it not 3 each and 2x and the fifth? Because number of 3 is 3.
Letters throw us all off.
Lord, I'm so lost. Will you go
Okay,
slow?
why are we getting lost in this stuff here?
I'm stuck on the yellow part. The plus 3e to the 3x.
Yeah, derivative of e is just e, but then we have to take it times whatever the derivative of the power is. It's a chain rule.
Okay, yeah, I get that.
So this part here is just derivative of the front times the second.
I get that, yeah.
Plus the derivative of the second, which is e to the 3x times 3, because it's a chain rule.
Oh, you simplified it.
Oh, yes, that's why we're saying he wrote it different. He just simplified
I
it.
got it. Okay.
Word's good.
Word's confused.
That's 12x. What?
It's okay, they're just not understanding things.
Word, he changed it on us. He didn't.
I didn't realize just putting a 3 in the back versus front would just cause a mind melt.
I wrote it down. You're getting all worked up right now.
Well, it's still confusing that we're getting caught on the chapter 1 stuff
I don't
yet.
even need to ask questions. I just was
You're
looking
getting awfully worked up and it's really triggering.
And you don't set everything else up?
All right, and factoring this because we got to find inflection points. I'm going to pull out a 12e to the 3x.
Yeah.
So this turns out to be a 2. This turns out to be a 3 and an x. There's no way to make this thing a 0, so there's no inflection point. And set this thing equal to 0, and this x, this inflection point ends up being a negative 2/3.
Thank you, Jared. It's great to have your cuts. Why did you explain that to me?
It's 2 plus 3x.
So there
equals 0,
wasn't
and you
an
solve.
inflection point on the first part, right?
Good.
Oh yeah, no, never mind. Never mind.
And with that
Sit
one,
over there.
Can I turn?
since there is an exponent,
I'm not even gonna-
it's 0.
It didn't count. Like it didn't count on that one on the outside. I can't make that thing 0. Like there's no way to make it.
It has to have a variable, right?
Yeah,
Or maybe it does, but you can't do it.
I can't do it because there's no way to make that equal 0. So I can't. It doesn't count.
So my correction is going to be on paper.
What's the other word they make?
That's fine.
We know what you meant.
Okay. All right. All right. I'm moving on. Okay. Okay, we have a couple new things today that we're going to cover. We have to cover graphs today. So I'm going to cover the real basics parts of graphs. Everything up till now has just been derivatives. We've done derivatives since chapter 1. It's been a long time. What we're doing today is looking at the graph portion of it and kind of going back to the basics. There's a couple things we have to talk about with graphing and derivatives and all that good stuff that some people just don't realize that we have to just kind of talk about. And this is the part that can be kind of a helpful thing if you have a graphing calculator or if you have access to a graph. This could be a shortcut for figuring out, critical points and all that good stuff. So that's what we're going to look at. It's not the end-all be-all because you still have to interpret the graph and hopefully you know exactly what the numbers are. But I'm just going to kind of show you some details. Does anyone still need this, though? Okay, the other problems in the homework should have been a lot simpler. These were just the challenging ones. The other ones, I pulled these out of the book. Every one of those problems were out of the book. It just, those were mixed in there, and I was like, we'll probably have to talk about them, and I figured we would. So, all right, let's move on to the next part here. All right, so state the critical points and inflection points. So if I were to give you a graph, so I'll just kind of draw a mock graph here. Again, if you have just normal notebook paper, just draw the generic thing I'm drawing here. So this is what I'm going to be drawing. I'm just going to draw something very basic, okay? Something like that. The idea here is what a critical point is and an inflection point. I want to show you the difference between them when we look at a graph. This graph is representing my normal function. This is the normal function on my graph. It's a very smooth, continuous graph from the left side to the right side. So finding the number should be pretty straightforward. It is oscillating up and down. Okay, so critical points on this graph is when the slope would be 0. So that's a critical point. So critical points are when the slope is equal to 0. That's what you're noting on critical points. So on this case, I can figure out the critical points real easy. It's when these are the points where my slopes are 0. And you just tell me those x values where the slopes are 0, where it like hit a hilltop or a valley. That's what max and mins are. They're basically just where the slopes are 0. They could be local or absolutes. It doesn't matter. It's just one of those things you need to be able to identify. So on this problem, what are the points, what are the x numbers that would give me these critical points? Like what is this number right here?
4.5.
Negative 4.5. Okay, so one of those is negative 4.5, 4.5. What's another one?
0.5.
Positive 0.5. And the other one? What is that? 1, 2, 3, 4, 5. Let's say 6. Let's say 6. Those are my critical points. It's when I hit the peaks and valleys. Now, obviously, some of these are absolutes. Some of these are kind of locals. Like we could go higher and lower at certain other points. Local, or what the book refers to as, instead of local, it calls it a relative max or min. Like this point's a relative. It's not the highest point on the graph, so it's called the local max, because this point over here is the tallest. That's the absolute. This is the absolute maximum, right? All right. 6, almost erased it. All right. So now, the inflection points is when it suddenly changes from concave down to up and to down again. It's the points in between. So this is the tough part. So question.
So for absolute maximum, would it be like if it's off the graph, you don't know where the maximum is at?
No, it has to be a solid point. It can't be just like an arrow pointing upwards. It's got to be like an actual peak.
So we do have a
So-
max
Well,
and
you
minimum.
do know that there's a curve out there.
Oh, if you know that it's curving back down, yeah, and it's off the graph, you might have to go find
Okay,
it.
like you have minimum, maximum right here, that would be the
Relative,
okay.
yeah. The absolute is like there's nothing higher. Like on that one, there is nothing higher than that left
Will you
point.
eventually find
But
both
is it-
absolute and relative?
Yeah,
Does that one
that's something we
have
do in
an
this
absolute
chapter.
minimum though?
Yep. What?
Does that one have an absolute minimum?
No, it has a relative, because this is kind of a relative, or what they call a local minimum. But then these arrows keep going down forever, so it has no absolute
Didn't
minimum.
you just say it has to be a specific point?
It has to be a specific point to be an absolute.
In this graph, there is no absolute minimum.
There is no absolute minimum, but there is an absolute max. Yeah. So it can be an arrow. Arrows don't count.
So if it's a continuous graph, like both ends are facing the same way, you're always gonna have
You're gonna have something in there. You're gonna have
So what if they're
you're gonna have an absolute at some point.
But if they're going opposite,
Yeah.
then you're gonna have only
Relatives.
relatives.
Yep, that's a good way to think of it. Yep. Yep. Those are the little things we're gonna talk about in this chapter. Okay. All right. Now. Okay, so on this one, the inflection points is when it changes from concave like down and up. So here's the idea. How I explain concave up and down, I did this last week, like last Wednesday. This part over here, this is concave down. This is concave down. The water would pour out of the bowl. This part is concave up. And this part over here is concave down. Does that make sense what concave down and up mean? Like, does it hold water or does it dump it out? And the inflection point is the point when it switches. So the inflection points
Basically
here.
our x-axis.
Yeah, I mean, in this case, it's probably about right in this range. There's an inflection point. It's right in there, and probably about right in here again, because it changed from concave up to down. That's an inflection point. It changes direction. Now, how we find these points, and that's what the second derivative comes in. It tells us what those points are. That's what we're finding. Now, the questions we've done up to this point, it's just, can you spot them? Can you find a second derivative and kind of set it equal to 0? But we've never checked them yet. We never went back and went, well, is this really an inflection point, or did it just kind of stay with the path it was going? It just kind of leveled off all of a sudden. So that's something you got to think about. All right. So in this case, yeah, we have a couple. So it's still be x numbers. What is that? Like negative 1.5. So x could be a negative 1.5 roughly. Again, these are all like approximations. And yeah, 2.5. I'll go 2.5. Approximately, that's where my inflection points are happening. I'm ballparking.
Is that all we have to do on the question?
Yeah. So on the question, it's going to give you a graph. It'll give you some type of graph. It could be a first derivative graph, it could be a second derivative graph, or it could be just a normal function graph, and it'll ask you where's those critical points, or where's that inflection point? So I'm going to do another one of these here in a second. But do we agree that this graph originally was a first derivative graph? Or a normal function graph, sorry. Yeah, I ballparked it. Yep. So this is a normal function graph. So finding the derivatives, you have to figure out where the slopes are. The next example I'm going to do is I'm going to give you a problem where I just give you the first derivative graph. We have to do the same stuff. And that's a more challenging one.
Tomorrow?
No, right now.
Get to it then. Warren.
Okay, all right. Let's go to it. So next example here. Okay. All right, I'm going to take a screenshot of that.
So is it easier to identify the inflection points on when it's graph? Like on graph?
Yeah.
Because you can almost pick anywhere when
So when you have a normal graph, it's super easy to figure out inflection and critical points because you just look at those peaks and valleys and stuff. But when you have to actually take a derivative and do like the work like you guys were doing the last stuff, that's way harder. But it's more accurate because now we can find exactly the number where it happens. Not like guessing like 2.5-ish or 1.5. We know exactly it's like -1/3. That's where it's actually changing directions.
for the inflection point, you could have guessed any.
Yeah, I could have guessed anywhere in that range. You could have said, like, I could see the argument, like, well, it looks like it's 3 to me. Okay, 3. You're in the ballpark, right? But when we actually do the derivatives, then you actually have to figure out the real numbers. So that's what we were doing those last assignments. So let's do one more. This is my last graph of the day. This is my last problem of the day.
Yes.
All right. So, so let's take a look at this graph. So I'm just let's pick something. Yeah, let's go opposite. I like that idea. Let's do something like this. Okay.
Now we got no option.
So now this graph, what I'm providing you here, is the first derivative graph.
That's what I like to call the algebra.
This is the first derivative graph. Now I'm going to explain the difference here. This is not the original function. This is the derivative of the original function. Okay? So here's the idea. This is representing slope at all moments. So critical points on the first derivative graph isn't just peaks and valleys. It's where your graph actually hits 0. These are the critical points on a first derivative graph because the slope would be 0 at those moments on the y-axis. So in this case, the critical point on this graph, again, this is different than the first one. Critical points on this graph is -3.5. And what is that? 1, 2, 3, 4, 5, 6. Those are my critical points. Because again, this is representing the first derivative. It's not the original function. And now to figure out the actual inflection points. And this will kind of throw you off. The inflection points now, it's when so on this one now, on the first derivative, it's when you have a peak and valley on a first derivative graph. So this point and this point would be the inflection points.
-3.5.
So -3.5 again, and what is that? And
Why? I don't
2,
get it.
2.5, 2 or 2.5.
Why is it not
2.25.
Because this is a first derivative graph.
I get it.
So because on a first derivative, right, this is all the slopes kind of happening here, and an inflection point would be the slopes of the first derivative. So because you take the second derivative, so you find the slopes of this graph. So that's what inflection points are. They're the slopes when this thing would hit 0.
So Ward, okay.
So
First derivative graphs are always opposite.
what?
First derivative graphs are always
Like
opposite.
this?
Yeah.
No, I mean the first derivative graph could have been anything. I could draw anything I wanted to.
Then you just picked it.
I just picked it at random. I just picked this graph at random.
You just said, oh, I'm just gonna do a first derivative graph.
Yeah, I'm just going to do a first derivative graph. Just so you can see that first picture I did, and you can see this one. These are the two types of problems we got to be used to.
Okay.
Okay, all right. Your Google question of the day is live. I think it went live about 10 minutes ago. It is doing one of these, and all you're doing is interpreting where the critical points are and where the inflection points are. You're guessing. And I tried to mark the numbers and put some digits in there so you could get a better sense of where it's at. Again, you're ballparking where critical and inflection points are. That's what you're doing. And I believe the graph I give you is a first derivative graph. It's one of these. It's one of these.
It is.
It's one of those. I'm pretty sure.
Does it tell us?
Let me. It is? Okay.
And
Why did I go to my drive? That's not
I got these.
That's all I ever do in this class.
those
Yes.
be.
Brandon, you confused? What's this?
First derivative.
One. One.
Okay, I'm gonna show it up here. Here's the problem you're gonna have. I'm gonna put it really big up here on the marker board. If it works.
Are there arrows going or is this just air?
The arrows keep going. So I'm not worried. Just give me the ones that you can definitely see on the graph.
This is -1, 0, 1, 2, 3.
Oh, I think it froze. My computer froze. Oh man, come on.
Local math and local math because the arrows are going like this, right?
Yeah, so.
So, Mr. Wood, when like
-1,
critical
3, 9.
points and the inflection points are the same, it's just going like,
What about
so, like that, right?
So it just wants critical and not deflection?
I think, does it just ask for critical on that one?
I don't know.
It might just ask for one. I don't remember. This was supposed to be your Google question on Friday. I don't remember what I submitted. I just changed the date.
Which
So.
critical points does F have a local maximum?
Okay, there you go. So, yeah.
At about.
Wait, so we don't what?
Yeah, how are the arrows? Are they opposite?
Yes.
So they're all.
I've already do
I
that shit.
believe we can drill.
There you go. That's the picture you guys had.
This is, I don't know.
So it's minimum at 9,
It doesn't
right?
really matter down here because we're not gonna.
No.